Welcome. This lesson is about accuracy and precision in electronics. For me to think about accuracy and precision, it helps best to think about a target. This is accurate, all the bullets hitting the center of the target. This is precise, all the bullets hitting close together, but it's not accurate. So what is more accurate? 47,000 ohms, 47 kiloohms, 47.000 kiloohms? Are they all the same or are they different? Accuracy is how close to the true value a measurement is. It's measured by the number of significant digits. Significant means making a difference. So the only significant digits are any non-zero digit, zeros that are between two significant digits, and any final or trailing zeros only in the decimal portion of a number. For example, how many significant digits are there in these numbers? The best way to learn is by examples or practice. First one's easy. They're all non-zero digits, so they're all significant. 347 has 3 significant digits. 8,074, the 0 is between 2 non-zero digits, so it's also significant. So there's 4 significant digits in the second number. For the third number, the 0 is not significant. It's not between two other numbers. It's not after the decimal. So in the third number, in 890, there's only 2 significant digits. How about in this one? Only has 4 significant digits. That final 0 is not significant. 3 significant digits here. How many in this one? Yeah, that final 0 is trailing. It's after the decimal, so that is significant. So 4 significant digits here, 3 here. In this number, these zeros are after the decimal, but they're not trailing. They're not at the end of the number, so they're not significant. So only 2 significant digits in this number. But in this number here, again, these 2 zeros are not significant, but the final one is a trailing 0, so it is significant, and it's after the decimal. So 3 significant digits here. And in this one, only 2 significant digits. The 2 most important ideas I hope you get out of this lesson: measurements cannot be more accurate than instruments can measure. You have to depend on your instrument. It's important to use equipment that can measure as accurately as you need. However, the more accurate tools cost more usually. So you should invest in equipment that is good enough for what you intend to use it for. You can spend a lot of extra money on something you won't really need, but if you really need that level of accuracy, you need to invest in that tool. Second main idea is that calculated answers cannot be more accurate than the inputs used. When we think about precision, precision is how close repeated measurements are to the same value. It's like the target. If all of the bullets are hitting in the same spot, they're precise. What we really want is precision and accuracy, where they're all hitting in the same spot and all at the correct value. Precision is measured by the place value of the last significant digit, and we state it as precise to the nearest whole number or the nearest tenth or hundredth and so on. When adding or subtracting values, maintain precision. Here's an example of adding 2 voltages. The first one, 4.7 volts, is precise to the nearest tenth of a volt, and it's accurate to 2 significant digits. The second number, 6.2 volts, also precise to a tenth of a volt and accurate to 2 significant digits. When we add those up, though, you get 10.9 volts. When you're adding or subtracting, you keep precision, which is determined by place value. So 10.9 volts is what we would report as our answer. But when multiplying or dividing values, you maintain significant figures. For example, 12 volts multiplied by 32.1 milliamps. 12 volts has 2 significant digits. 32.1 milliamps has 3 significant digits. So our answer cannot have more than 2 significant digits. So when we do this on a calculator, the calculator will report 385.2, and volts times milliamps would give us milliwatts. But that has too many significant digits. We need to only have 2 significant digits, so we report our answer as 390 milliwatts, because the 0 at the end is not significant. So what level of precision does each of these numbers have? Well, the first number is precise to the nearest ohm. Also, the second one to the nearest ohm. The third one, though, because that 0 is not significant, we would report its precision as accurate to the nearest, not to the nearest milliamp, but to the nearest 10 milliamps. And this fourth number, also the final zero is not significant, so we would say it's precise to the nearest 10 ohms. 53.7 volts is precise to the nearest tenth of a volt. 53.70 volts, though, is precise to the nearest hundredth of a volt. 2.03 amps is precise to the nearest hundredth of an amp. And 0.0012 amps is precise to the nearest 10,000th of an amp, or tenth of a milliamp. 0.00120 is precise to the nearest hundredth of a milliamp. And 53.000 volts is precise to the nearest thousandth of a volt, or millivolt. Using engineering notation helps you to determine how many significant digits a number has. It's an easy way to do that. It's like scientific notation. However, in scientific notation, you always have one number before the decimal and then any number of digits after the decimal, and then you report an exponent as any digit. But in engineering notation, you'll either have 1, 2, or 3 numbers before the decimal, and the exponent will always be a multiple of 3. For example, 72.45 times 10 to the third, or a number times 10 to the ninth, or they can be negative numbers to move the decimal the other direction. 10 to the negative 3, to the negative 6, 10 to the negative 9, for example. Engineering and scientific notations get rid of non-significant zeros. You move the decimal over and it gets rid of non-significant zeros. For example, 22,000, you'd move the decimal for an engineering notation to 22 times 10 to the third. So it tells you, oh, there's only 2 significant digits. In scientific notation, you can move the decimal over further. It'd be 2.2 times 10 to the fourth. But again, in that number, there's 2 significant digits. Or you could do scientific notation, and it would be 3.70. But again, you put that final trailing zero as significant. So reports 3 significant digits. So metric prefixes are used to replace the exponents. Instead of saying times 10 to the some number, we can use a metric prefix before our unit, and makes it quicker and easier to report what the values are. For example, 10 to the 3 is kilo, abbreviated K. 10 to the 6th, mega, capital M. 10 to the 9th is giga, or capital G. And 10 to the 12th is tera, or capital T. And those are generally about as high as we go in electronics. There may be some higher, but these are the prefixes you usually see. You can also go smaller than the base value. 10 to the minus 3 is milli. 10 to the minus 6 micro. The symbol there is actually the Greek letter mu. It looks like kind of like a little letter U. 10 to the minus 9th is nano. And 10 to the minus 12th, pico. These are, again, the typical values you see in electronics most of the time. So for some practice, let's look at these numbers. 72.45 times 10 to the third ohms. How many ohms would that be, or any of these numbers? Just take a minute and just do those. You can pause the video, and when you have them, unpause it and I'll show you the answers. And there they are. So after teaching this for my students, I'm assigning them some worksheets to practice on because I know it helps to have practice. I give them a significant figures worksheet and then an engineering notation to convert units to engineering notation, and also using the metric prefixes, and I have another worksheet on engineering and scientific notation. So final word, just remember measurements cannot be more accurate than instruments can measure. And calculated answers cannot be more accurate than your inputs used. Don't report calculated answers as more accurate or precise than they should be. Otherwise you give the impression that you know it more accurately than you actually do. Also, every electronic component is imperfect and has a tolerance range. For example, you may have a resistor that's a 100 ohm resistor. However, it may not be exactly 100 ohms. Every resistor has a tolerance range, whether it's plus or minus 5%. So it could be anywhere from 95 ohms to 105 ohms. Or maybe it's plus or minus 1%. It could be a little more accurate. But there will be always a tolerance range. So measurements are usually off what calculations say they should be. And the more components that make up a circuit, and each tolerance range could be a little bit off of what the number is supposed to be, that affects our final answer. So in practice, often you can round just your final answer and it'll still be close enough. You can use lots of those decimal places on your calculators and still get a close enough answer in practice. However, I think it's still important to correctly calculate using significant digits, accuracy, and precision when you're designing and repairing electronics. It's always best to keep your numbers what they should be, rather than using whatever your calculator says. So hopefully this has taught you a little bit more about accuracy and precision in electronics and how to correctly report your values. Thanks and have fun.